All right, let's dive right into this explainer. When we think about high-speed rail, our minds almost always jump straight to those sleek, futuristic trains just rocketing across the landscape. But the real magic, the incredible engineering that actually makes traveling at those crazy speeds possible, it's not just the train. It's the meticulously designed track hiding right beneath it, built up from the very dirt all the way to the steel rails.
Sure, the train itself is what catches the eye. But the actual star of the show here is the complex track system totally buried beneath the surface. To safely absorb the massive dynamic loads and intense vibrations of a train flying by at 350 kilometers per hour, engineers literally have to treat the entire track, from the deep subsoil through the protection layers, all the way up to the sleepers, as one massive unified system.
So, here's our roadmap for today. We're going to take a bottom-up approach. We'll start with the hidden foundation, then look at protective layers and geotextiles, move up into engineering the traditional ballasted track, look at the big shift towards slab tracks, and finally wrap up with modern slab track systems.
Part 1. The hidden foundation, looking at the subgrade and sub-ballast. Let's start deep in the dirt. Now, you might be thinking, hey, high-speed passenger trains usually have axle loads under 18 tons. That's relatively light, right? The foundation shouldn't be a huge deal. Well, actually, any weakness in that subgrade is pretty much guaranteed to mess up the strict track geometry above it. A weak foundation basically guarantees track failure down the line.
Look at how the pressure distribution fundamentally changes the second you add a protective layer. Without it, that forced transmission area is dangerously narrow. The pressure on the soil spikes, and you risk massive shear failure, plastic deformation, basically a dangerous disruption of the whole track geometry. But when you add that subballast protective layer, it spreads the load outward like a giant shield. It drastically reduces the stress on that sensitive subsoil.
Moving on to Part 2, protective layers and geotextiles. To manage all those extreme pressures we just talked about and protect the earth formation underneath, engineers bring in the absolute unsung heroes of rail infrastructure.
Enter geotextiles. These are inserted right between the underlying soil and the protective layers. Now, they do a lot. They provide vital separation, reinforcement, and drainage, but their absolute most crucial job? Filtration. Think of a geotextile like a highly specialized heavy-duty coffee filter. It stops fine mud and soil particles from pumping up into the clean track ballast above it while still letting water drain right through. They are absolutely essential for making sure the track maintains its required bearing capacity over its 20-plus-year lifespan.
All right, Part 3, engineering the ballasted track. Moving up from the subgrade, we hit the traditional gold standard. This is the backbone used on roughly 90% of high-speed lines across Europe. So what exactly is ballast? Well, spoiler alert, it is definitely not just random gravel scooped off the side of the road. For high-speed lines, it has to be highly specific, incredibly hard rock, almost exclusively granite or basalt. It needs massive resistance to attrition, so it doesn't just grind down into dust under all that intense vibration. This carefully sized, crushed stone creates a stable, perfectly elastic bed that distributes the load, drains rainwater instantly, and holds the track geometry exactly where it needs to be.
And the engineering consensus across Europe is actually remarkably unified on this. From France to Germany to Spain, high-speed lines universally demand a strict minimum ballast depth of 300 to 350 millimeters. If you want to safely handle trains pushing past 300 kilometers per hour, this deep, highly specific rock bed is completely non-negotiable.
And there's hard data to back this up. Extensive trials at the FAST facility over in Pueblo, USA, proved exactly why these specs matter so much. They discovered that right at 300 millimeters of ballast depth is the absolute sweet spot. That depth requires the least amount of track geometry correction over time. It literally outperforms thinner 150 millimeter beds and surprisingly even thicker 450 millimeter beds. You combine that 300 millimeter ballast with a 150 millimeter bituminous subballast layer, strictly use granite or basalt, and widen the shoulder ballast up to 700 millimeters, and boom, you've got a track that can handle some serious speed.
Which brings us to Part 4. The shift to slab tracks. Now here's where we hit a major engineering plot twist. Traditional ballasted tracks are amazing, but they definitely have their limits, especially when we're talking about maintenance and tight space constraints, like running high-speed trains through underground tunnels. And that limitation? That's exactly what drove the engineering world to develop ballastless or slab tracks.
The big engineering leap here really boils down to elasticity versus rigidity. With a ballasted track, the crushed rock gives you elasticity. It allows for up to 2 centimeters of settlement over a 10-meter stretch, which is totally fine because machinery can just come in later and tamp the stones back into place.
Because of that flexibility, you only need to secure the substructure about half a meter deep. But the second you replace those elastic rocks with rigid concrete in a slab track, the tolerance for settlement becomes virtually zero. You can't just easily adjust a solid block of concrete. So your earthwork substructure has to be completely flawless, secured a massive 2.5 meters deep to prevent literally any movement whatsoever. And finally, Part 5. Modern slab track systems. Let's look at how engineers actually pull off these zero-settlement rigid concrete lines, using some of the most advanced construction methods out there.
The Rheda 2000 system is a textbook example of this. Originating in Germany, this is actually the world's most popular slab track system. What it does is use modified twin-block sleepers that are cast directly into a monolithic concrete slab in one single pour, no gaps whatsoever. That design gives it an incredibly low overall height, which makes it an absolute game-changer for threading high-speed lines through tight tunnels. Alternatively, you have the SATO design, which takes a totally different material approach. It's a bit more expensive, but it's highly effective. It uses these unique Y-shaped steel sleepers. Engineers weld these sleepers to a flat steel strip using tie bolts, and then the entire matrix gets securely embedded right into an asphalt-bearing layer. That locks the sleepers solidly in both the horizontal and vertical directions.
And we can't forget the Bogl system. Instead of pouring concrete out on the site, this design relies on massive, high-tech, prefabricated steel fiber concrete plates. We're talking plates that are 20 centimeters thick and 6.5 meters long. Because they are manufactured under incredibly strict factory conditions, the track positioning is perfectly exact before the materials ever even arrive at the construction site.
So here's the thought for you. The next time you settle into your seat on a high-speed train zooming smoothly across the countryside at 300 kilometers per hour, I want you to ask yourself, what is actually under me right now? Are you riding on a perfectly engineered, elastic bed of crushed basalt, carefully draining the rain away? Or are you soaring over a rigid, prefabricated, monolithic concrete slab anchored 2.5 meters deep into the earth? You know, it completely changes how you experience the journey once you realize the sheer scale of monumental engineering hiding right beneath your seat. Thanks so much for joining me.